Yeah, did someone say?
No.
Oh, okay. So here's where we are. So we're doing particle kinematics.
Can I still ask more questions?
Yes.
1 second, let me.
A homework question?
Yes. 1 second, please. Internet is.
So we have a camera that's mounted to the car. So whatever the car's acceleration is, that's the camera's acceleration. And we'll think of, so I'm going to call O the object that falls, that's dropped. V, I guess, is the vehicle. And G is the ground. And we know that the acceleration of the object relative to the vehicle is -5, -11.5. And we know that since this object is in free fall, the acceleration of the object, if you're watching it from the ground, would be 0, -9.81. The relative motion equation says the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the vehicle plus the acceleration of the vehicle relative to the ground. And you can check that as, does this hold, this fraction multiplication? And it does. So we know that this is the right order for this relative motion equation. And so then we have 0, -9.81 is equal to -5, -11.5. And we're looking for the acceleration of the vehicle relative to the ground. And now just do the algebra. You can do it. You can separate this into X and Y equations and do it. Or you can do it in full vector form. But what you get is that the acceleration of the vehicle relative to the ground is equal to 0, -9.81, minus -5, -11.5. And the X is 5. That one's easy. And the Y is -1.69.
Is that positive?
Positive. Sorry.
No, can I ask anything else? I did show up in the homework for due time, but I was checking my answers and I found a mistake. Is how much does the homework count?
Okay, so the daily homework, I am not checking those. Okay, you are it's your responsibility to convince yourself that you're doing it right, or bring it up in class, and I'll talk about it. Okay, so I mean, I wish I was grading everything. It's just too much, So if you turn those assignments in, you get full credit, but you should figure out how to do those problems right, because that's what the exam questions are based on. Okay, that's how the daily assignments work. Question?
If we notice a mistake on the answer sheet, we'd let you know.
Yeah, that would be great. Yeah, if you email or send me something through the instant messenger, that would be awesome. Yeah. Yes.
What problem is that?
This is number 13, I think. Yeah, 13.
Perfect, that's the one I wanted.
Oh, okay, good. Any other homework questions anyone wants to see? So this is very much like, I mean, it's exactly the same thought process as the example I did, just the numbers are a little different. Okay. So going back to the topic that we're on, we're doing particle kinematics. Remember, everything we're doing here is for non-rotating coordinate systems. And we first dealt with acceleration as a function of time. And you think of that as defined as the time derivative of the velocity. And you think of that as the second time derivative of the position. And then the second thing that we talked about is the chain rule. And that's if you can come up with the velocity as a function of a position variable. And then third, we talked about relative motion. And we've done all these. And the last piece of this is circular and spherical motion. And so this is what we're going to talk about now. And these two are inextricably linked. Oh my God. Why did I say that word? Inextricably linked. You can't disconnect that link. They cannot be extricated from one another. For rigid body motion. Okay, so circular and spherical motion. What I don't have in my notes here, unfortunately, is a definition of, so the first thing that we have to define is angular velocity. Okay, and so what is like the definition of angular velocity? For like in an infinitesimal time interval, an object moving in circular or spherical motion always carves out a part of a circle, you know, an infinitesimal part of a circle, arc of a circle, let's say, of a circle in a single plane. Okay, so let me, So let me try to get at what I'm describing here. Okay, so if something's in circular motion, if it's moving in a circular path, then, I mean, of course, in some tiny amount of time, that object is remaining doing an arc of that circular path. Okay, so let's say that an object is going through a circular path like this. Okay, you can define the plane this way, and in an infinitesimal time interval, it's going through an infinitesimal arc of this path like this. Okay. There's no doubt that that arc is in a single plane and that it's part of a giant circle, right? By definition. But what about something that's moving through a path like this? Okay, so imagine that it's confined to this spherical path. Okay, and it's doing all this. Okay, if you look at an infinitesimal time interval, it goes an infinitesimal distance and even though the overall path is not in a single plane, this arc is in a single plane. So this path is circular in a plane. So the red infinitesimal arc is part of a circle in that plane. Duh, right? That's obvious if you're understanding what I'm saying. And this could have been clear, but I'm trying to clarify this. So what about this? Circular, it's kind of an obvious thing. Spherical, it's not so obvious. The path is not circular or confined to a plane. But that red infinitesimal arc is circular and confined to a plane.
So what is infinitesimal and not infinitesimal? When does it become not infinitesimal?
I mean, you have to think of that as like a limit. So, okay, well, yeah, the infinitesimal arc is a limit. So as soon as you go a billionth of a trillionth of a second, that's the cutoff, a billionth of a trillionth of a second. So in the limit, it's part of a circle, but it's kind of like sort of like a circular analog of this. I don't know, don't write this in your notes. I'm gonna erase this, but it's kind of the same thing as finding like a tangent line, you know? Like this thing at this point isn't a straight line, right? But zoom in and it's closer to a straight line, but it's still not a straight line. So zoom in and it's even closer to a straight line, you know? And in the limit, it's a straight line and that's the tangent line at that point. Okay.
Given
Yes.
the following during the session, could you please scroll up to forward this as angular velocity, please? Okay, great, thank you.
Mhm. Okay, so the angular velocity. So if you identify the circle or the circular path that infinitesimal arc is part of, then the magnitude of the angular velocity is the change in theta around that circular path divided by the change in time, the derivative with respect to time of the change in angle, and the direction of the angular velocity. So this is a vector, this angular velocity, and the direction goes according to the right-hand rule. Okay, and this angular velocity is a vector, and we're going to describe it as, we're going to represent it with the Greek letter omega, lowercase omega. Okay, so let's do an example and see how this works for a circle. So let's say our coordinate system, well, let's say this object is moving in a circular path like this. Dang it. And let's say that our coordinate system is this. X goes this way, Y goes this way, Z goes this way. And let's say that the object moves with a constant speed and it completes 1 revolution per second. What's its angular velocity vector? Okay, so we're going to go based on these two definitions. The magnitude, is the change in angle divided by the change in time. This is in radians per time, by the way. Anytime you're using derivatives with angles, you need to be using radians. And this is time, whatever it is, we'll use seconds. Okay, so if it's completing 1 revolution per second, 1 revolution is how many radians? What? 2 pi. And it's doing that every second, so the magnitude is 2 pi radians for every 1 second. So 2 pi radians per second. And now we have to think about the direction. Well, this goes according to the right-hand rule. So have you all seen the right-hand rule before? Anybody not seen that yet? So have your fingers curl in the direction of the motion. Your thumb is the direction of the vector. So in this case, I should have given a different example. I'm like looking for confirmation and everybody's like, this sucks. But no, the direction of the vector is in the negative y. And so as a vector, this is 0, negative 2 pi, 0. And usually in this class, angular velocities are just going to be things that are given in the problem because there's not like a real, in most problems, there's not a really like elegant, quick way to calculate the angular velocity.
Elegant.
Okay. Well, anybody have any questions about that? That was a mess. I was missing that part in my notes, but I'd be happy to talk about it for a minute or two. Is everyone following the sort of idea that I'm getting at here? It's easy to picture for a circle. You can just kind of imagine that if this thing is moving all over the surface of a sphere for a limiting infinitesimal time interval, you could identify the circular path that that's a part of, okay? Each instant is confined to a single circle, and you would define this the same way, okay, once you identify that circle. All right, so once you have the angular velocity, here are the two circular and spherical motion equations that relate. I guess I should define the angular acceleration too, but that's going to be easy to define. So we're going to call this lowercase alpha, and this is also a vector. It's important to remember that angular velocity and angular acceleration are vectors. And the angular acceleration vector is just defined as the time derivative. Yeah. Just the time derivative of the angular velocity vector. Okay, so once you have those two things, the circular and spherical motion equations relating angular velocity and angular acceleration to translational velocity and translational acceleration. So these are the circular and spherical motion equations. Velocity of the particle is equal to omega crossed with r. I'll tell you what these variables mean in a second. And the acceleration is equal to alpha cross r plus omega crossed with the quantity omega cross r. So we're going to use these two equations all the time. Omega is the angular velocity vector Alpha is the angular acceleration vector. And R, okay, so the devil is in the details with all of this stuff, and you need to be able to give mathematical definitions for all of these, like P vectors, R vectors, row vectors, all this stuff. Like, there are all these things that are going to be kind of similar, and you have to absolutely know the difference between these things. The R vector is defined as the vector from the center of the circular or spherical motion to the particle. It's R for radius, but a radius is just a number. This is a vector, okay? How does this relate to what you learned in Physics 1? This red is the tangential acceleration. And the green is the centripetal acceleration. Okay. And to remember this equation that we're going to use all the time, I think this just popped into my head in class one day, like 20 years ago, and it's still what I use. So I don't claim it's like the most meaningful phrase, but I always think of this as all ripe watermelons will rot. Okay, so all the alpha, ripe, omega is watermelons will rot. Okay, somebody like 10 years ago or whatever was like, why you gotta be so pessimistic about it? How about all ripe watermelons will rock? So you can use that one too, but this will just help you remember the order. Okay. These parentheses here in the centripetal acceleration part are important because if you do omega cross omega, what's that? 0, yeah. You definitely would be happy if you have a way to calculate the cross product on your calculator instead of doing it like sort of element by component by component every time you do it. So I can help you do that if you have a question. If you have a TI-89 or a TI Inspire, it's a built-in function called cross P. So that's great. If you have an 84 or an 86 or an 83, then you have to make a program that does it. But I can give you the code and I can help you get it filled in after class or in office hours or whatever. Okay. In circular motion, omega and alpha are parallel. And both are perpendicular to the plane of the circle. in spherical motion, omega and alpha are not parallel. Okay, let's do an example. So let's say that a child is on a carousel. With a radius of 2 meters. And at the given instant, it's rotating counterclockwise. With an angular speed, so a magnitude of the angular velocity of 2.5 radians per second. And let's say it's slowing down with an angular acceleration magnitude of 9.5 radians per second squared. And we want to calculate the velocity and the acceleration of, let me draw a picture. So the carousel is going around like this.
What instead of
And right at this point, where it's along the positive z-axis from the origin, that's where we want to calculate the velocity and the acceleration. Okay. Anyone have any questions about what we're trying to do here? So we're going to have to think a little bit about the definitions of angular acceleration and angular velocity. Is this circular or spherical motion? Circular. And so what do we know about the directions of angular velocity and angular acceleration? They're parallel, and the plane of the motion is the xz plane. Okay, so omega and alpha are both going to be along the y-axis somewhere, because of the right-hand rule direction and the fact that they're parallel. Okay, do you see that? The right-hand rule says, roll your hands that way. The angular velocity is going to be in the positive y direction. Okay, now the right-hand rule says that the direction of omega is the positive y. What about the direction of alpha? Negative. Yeah, that's exactly right. So anybody else see that? So think of it in terms of a difference equation. Alpha is defined as the time derivative of omega. Okay, so if this is slowing down, when you take your difference, you're going to get a slower number. You know, let's say, what speed is it going at this instant? 2.5. So it's going to be a slower number like 2 minus the earlier number that's faster divided by delta t. And that's going to be a negative, value. So, based on the fact that alpha is the time derivative of omega, the alpha direction is negative y. So now we can put this stuff together. Omega is 2.5 in the positive y direction. Yeah.
Wait, so if it was, acceleration was positive, like moving, like going faster, would it?
Okay, so for circular motion, if omega and alpha are in the same direction, the thing is speeding up. And if they're in opposite directions, it's slowing down. You can always think of that as like a rule. That's true with, it's the same with acceleration and velocity along a line, you know, translational velocity and acceleration. If velocity and acceleration are in the same direction, the thing is speeding up. If they're in the opposite direction, it's slowing down. And it works the same with these. Okay, so our omega is this. Our alpha, we figured out, is in the negative y direction. So that's 0, negative 9.5, 0. And now we can just use those two equations. Well, we have to figure out what the r vector is. So the definition of r, remember, is from the center of the circular or spherical motion to the object. What on this picture is the center of the circular or spherical motion? Yeah, the origin. I put the origin at the center. And this has a radius of 2 meters. So what's the vector from the origin to P? 0, 0, 2. Yep, exactly.
Do you only take a single point?
Yeah, this is for a single point. Yep. You have to do it point by point. Okay, so now we can say that the velocity vector of P is equal to 0, 2.5, 0, crossed with 0, 0, 2. Take that cross product and you get 5, 0, 0 meters per second. Let's look at the picture. Does it make sense that this object's velocity is in the positive x direction? Yeah, because that's tangent to the path at that instant in the direction of motion. And then the acceleration. So we're going to go all right. Watermelons. Will rot. And if you plug that into your calculator, you get, for this one, this is the tangential acceleration, that's negative 19.00. For the centripetal acceleration, you get 0, 0, negative 12.5. So first, let's think about these two components and think about if that makes sense. So the tangential, this says, is in the negative x direction. Would we expect the tangential acceleration to be in the negative x? Yeah, it's slowing down, so it has to be opposite the velocity vector. And then the centripetal acceleration is in the negative z. Would we expect the centripetal to be in the negative z? Yeah, because going towards the center of the circular motion is negative z. But the nice thing is, as long as you're, I think it's always a good idea to kind of sanity check stuff, but as long as you don't make any math mistakes, you never have to think about the direction of the centripetal, the direction of the tangential, anything like that. The vectors do all the work for you. And so the answer here is negative 19, 0, negative 12.5. God damn it. And that's in meters per second squared. Yes?
Yeah, just for the axis, like the X, Y, Z, is that just like the orientation we're gonna be using for this class?
We're going to be, the coordinate systems are going to move around a lot in this class. In math, that never really happens because in math, you don't care, there's no physical world to tie stuff to. So whatever orientation the coordinate system is, you might as well just imagine looking right at it. But to us, our coordinate system is always going to represent something in the physical world. You know what I mean? So a lot of times ours is going to be at a funny tilt or whatever. Yeah.
So for a problem like this, would we be able to use our P along the x-axis, or did we specifically put it along the z-axis for a reason?
Yeah, that's just because like whatever you're trying to analyze happens to be right there, you know?
Okay.
Yeah, you could put it wherever.
For this problem, it didn't specify, right?
The picture was supposed to be specifying it, that's all. But I have to specify it in some way for sure.
Okay.
Okay. Let's, okay, so now let's see, why does circular motion and spherical motion and relative motion go together so well? So let's think about a case like this, where you have a hinge connecting a body to the wall. And let's say at this instant, this first body is positioned like this, and this angle is 30 degrees. And then there's a second body connected to that one by a hinge. And at this instant, this first body has an angular velocity of 10 radians per second in the direction shown. And the angular acceleration is 5 radians per second squared. That same direction. And then the second body has an angular velocity this way. So omega 2 is 8 radians per second. And alpha 2 is the opposite of that with a magnitude of 20 radians per second squared. Okay, this is all in the plane, so it's hard to draw, it's a little cluttering on pictures to draw the actual directions of the vector. So notice whenever I draw a curved arrow, what I'm really saying is omega here has the direction of the right-hand rule of that curve, okay? So like this omega is pointing out of the page. This alpha is pointing out of the page. This omega is pointing into the page. This alpha is pointing out of the page. Okay, we're gonna do a lot of planar stuff. And whenever you're in the XY plane, all of these are gonna be Z components only. And let's say that we want to calculate the velocity and acceleration of this point P. Okay, so what we're going to do is we're going to name these joints. I'm going to call this one, so we already have P. I'm going to call this joint here A. And the connection with the wall, I'm going to call that point G for ground, okay, because the left side of this member is connected to the ground. And notice that A is in circular motion around this point G, okay, you see that? And P is in circular motion around this point A. If you ignore the motion of A, this P is in circular motion around that. Okay? So, using the relative motion equations, the acceleration of P relative to the ground, which is what we want, is equal to the acceleration of P relative to A plus the acceleration of A relative to the ground. And now we're going to use circular motion to calculate these individual parts. Okay? So first, let's calculate the acceleration of P relative to, no, let's do the other one first. What? The velocity and acceleration of the point P at the end. So let's calculate the acceleration of A relative to the ground first. Okay, well, we know that omega for this one is, I didn't give you a coordinate system, but I'm going to use this coordinate system with X this way, Y this way. That means Z has to be coming out of the page. Okay, so omega for this first body is 0, 0, 10. Alpha for the first body, based on the right-hand rule, is 0, 0, 5. R for the first body. Remember, for now, every time you use R, remind yourself what the definition is. It's from the center of the circular spherical motion to the point that you care about. So if we're trying to calculate the acceleration of this point A, the R that we want goes from this point G to A. I didn't give any lengths of these, did I? They need lengths. Let's say they are 1 meter long. Pretend I gave you that before. Okay, so the R vector is going to be, that's going to be 1 times cosine and sine of negative 30 degrees. So this is going to be 0.866, negative 0.50. That's cosine of negative 30, sine of negative 30, 0. And now we can put this all together. The acceleration of A relative to G is 0, 0, 5, crossed with 0.866, negative 0.50, plus 0, 0, 10, crossed with the quantity 0, 0, 10, cross 0.866, negative 0.50.
So like in,
Can I just write this down and then? So the acceleration of A relative to G is negative 84.1, 54.330. Question?
yes, for the decimals, do you want, would you have fractions in, exam response?
Yep. Okay, so that's the first part of this relative motion equation. Now we have to imagine that, like, ignore the motion of A and calculate the motion that P is making around A. Okay? So now we're going to the acceleration of P relative to A. Sorry, I know I'm going over. I'll make this fast. And so for this one, we're going to be using an omega, this other omega and this other alpha. So we have an omega of 0, 0, negative 8. An alpha of 0, 0, positive 20. An R vector that goes from the center of this circular motion, so this time it's from A to the point we care about, P. So that's just 1, 0, 0. And now we'll plug this into our formula, and the acceleration of P relative to A is 0, 0, 20, crossed with 1, 0, 0, plus 0, 0, negative 8, crossed with the quantity 0, 0, negative 8, cross 1, 0, 0. Plug that all in and you get negative 64, 20, 0. Now put it all together. The acceleration of P relative to the ground is equal to negative 84.1, 54.330, plus negative 64, positive 20, 0. And you get negative 148.1, 74.330. Okay, so you can see how naturally this comes about in machines, robotics, like all sorts of stuff. When you have multiple members connected by joints, You're using circular motion to figure out accelerations of the joint, and then you're using relative motion to figure out the total acceleration of the thing at the end. Okay, that's all.